因为过去那么远，人家提供你需要回来。西班牙可以飞回来。上面看的网站也不在上。右边啊，右边右边。摸了。哦，等我摸一下。
Sorry I'm late. Does anyone else have fun with trying to get down in lifts around the hour time? Okay. Okay then. Right, we're back to gases again. So we're going to just recap and go over the slides that we introduced at the beginning of last week but one, and recap on photochemistry before going into gas kinetics and the fundamentals of gas kinetics. So if we recall, the reason that photochemistry kicks off is that photolysis is initiated when photons of a sufficiently high energy impact on molecules that have weaker bonds than the energy supplied by the photon. So, if you recall, typical bond strengths of the order of a few hundred kilojoule per mole can have incident radiation of sufficiently high energy to break those bonds and initiate photochemistry. So in this example here, 495 kilojoule per mole of the O2 bond, of the delta O2 transition for ozone means that photons of a sufficiently high wavelength can lead to the photolysis of ozone. So the absorption of solar radiation and the Earth's radiation directly influence the energy balance. So in order to do that, you need to calculate the actinic flux. So what's the actinic flux? Can you remember? So what is it conceptually? Well, conceptually, the actinic flux is the flux of photons at any point from all directions. So it's not just the incident flux from one direction, it's from all directions. So you need to integrate across all of the various wavelengths and directions of the solar radiation. Now you can have, so the incoming radiation can be scattered by particles and gases. So what sort of scattering is it from particles usually? It's me scattering. And from gases? Yeah, okay. And you can have the direct solar radiation, the scattered direct radiation, the scattered reflected, and the directly reflected solar radiation. And in order to calculate this, at any atmospheric slab, you need to consider the latitude and the height of the sun in the sky. So the zenith angle and the latitude angle. And if you recall, the actinic flux is the solid angle integral. So you can see that the number of photons entering a layer is this L, dependent upon wavelength and the theta phi, times the cos phi, and the integral, and the increment ds d omega dt d lambda. So across all of the lambdas, space and time coordinates. And you multiply that by the absorption cross-section and the quantum yield. So we'll go back into the quantum yield in a second. So that solid angle geometry you're never going to need to actually calculate. You just need to appreciate that that solid angle geometry and the dependence upon the zenith angle and the latitude are important in calculating the amount of photons through a part of the slab, through an incremental thickness of the slab. So the quantum yield is the yield accounting for all of the possible processes. So there are a whole bunch of transitions or non-transitions from the absorption of the photons. So it can be the physical quenching of a molecule AB star, luminescence, ionization, dissociation, intramolecular energy transfer, so inside the molecule, intermolecular energy transfer between more than one molecule, isomerization, so the changing of the structure of the molecule itself, and direct reaction. And what we're considering when we're talking about photolysis is the dissociation. So it's if we're calculating the photolysis rate, we're only interested in this part here. So the quantum yield that enters into the photolysis calculation is the quantum yield for dissociation. So it might mean that for every incident photon, only 0.1 leads to a dissociation. So 10% of the time it might lead to dissociation. The rest of the time it can be absorbed intramolecularly, intermolecularly, or give rise to other radiation, for example. So if you remember, that quantum yield is only for the dissociation part. So the actinic flux, which is your I here, which is this integral, multiplied by the absorption cross-section, the quantum yield, and the volume, gives you the number of molecular dissociations. So the rate of dissociation, the dN by dt, is the integral across absorption cross-section, quantum yield, and the actinic flux. So if anybody talks about J values, they are the photolysis rates. So the J value is the... has anyone heard about JO singlet D? What might you think JO singlet D is? JO singlet D is the rate that ozone photolyzes to produce O singlet D. And O singlet D is the thing that goes on to make the hydroxyl radical OH. So J, what do you think JNO2 is? So what does JNO2 make? To make? So what does it make? So it photolyzes NO2, NO plus O. So JNO2 is the photolysis rate of the NO2 molecule to produce NO plus oxygen atoms. JO singlet D, it's not consistent. Sometimes JO singlet D is referring to the product, or JNO2 is referring to the reactant. But normally J has a subscript of a molecule that refers directly to the rate of the photodissociation. Now I've coloured this figure in from the one that you've got in your notes, that's downloadable from Blackboard, just to show a bit more clearly the incident radiation at the ground. So do you have more lower wavelength or more lower wavelength radiation at the ground, or less lower wavelength radiation? Less. Why? Why do you have less radiation, less shortwave radiation at the ground? So you've got more molecular absorbers of the shortwave radiation higher up. So you've got all of these, the more absorbers you have higher up, the less radiation that will reach the ground, more scatterers. So where does mean scattering happen generally? What wavelength? It's a wavelength comparable to the size of the scattering thing. So if your aerosol are 400 nanometers, then you're going to scatter light of wavelength of a few hundred nanometers. So you have more me scattering at a few hundred nanometers, and you have lots of molecular absorptions at the short wavelength regions, so you get less shortwave radiation at the ground. So more scattering and absorption higher up, less gets to the ground. And here you can see a big window. So what do I mean by a window? So here you can see at 30 kilometres you have an amount of radiation between 200 nanometres and 220 nanometres, and then you've got radiation from about 280 nanometres upwards. But you've got no radiation between 220 and 280 at 30 kilometres, because you've got all of those absorbers and scatterers above it. And you can see that you're eating into it, so you've got more molecular absorption at these wavelengths higher up. And then by the time you get to the ground, you've got nothing really left below about 290 nanometers. Now, if you look, the example of ozone, you've got the Hartley band, the Huggins bands, the Chapuis bands, and the Wolf bands of absorption. So where does ozone absorb most? In the Hartley bands. Strongest absorption is down at the Hartley bands. You've got Chapuis bands of absorption. So where might it absorb most in the troposphere? Well, if you go back to this figure here, in the troposphere, you've only got radiation from about 290 upwards, and your peak amount of radiation is around 320 upwards. And if you look here, it's from here upwards, you've got tropospheric radiation. From here downwards, you've got the Hartley band, you've got radiation in the Hartley band. So most of your absorption will take place above the troposphere, in the Hartley bands, but in the troposphere you will absorb from about 300 nanometers upwards. So you can see that the absorption cross-sections are going to determine where you get most of the absorption. Where is the photolysis of ozone strongest? So in the troposphere, where would you get most photolysis of ozone? If you remember, you don't get much from here, much below here. So your tropospheric radiation is above 300, and so most of your absorption from ozone is above 300. So you might expect that photolysis of ozone is greater than 300 nanometers in the troposphere. Would that be true? The answer is no. So why might you think that you don't get most photolysis of ozone above 300 nanometers in the troposphere? So if you go back to this equation here, the absorption cross-section times the quantum yield times the actinic flux. We've already said that in the troposphere, most of the actinic flux is greater than 300 nanometers. We've seen that the absorption is strong from the Chapuis bands and the higher bands for ozone in those tropospheric wavelengths. But the quantum yield is almost zero. So the quantum yield, which is required for the photodissociation of ozone, is almost zero at tropospheric wavelengths. But there's enough of the radiation around 290, 300. So 290, 300, where there's quite strong absorption in the Hartley bands, where the dissociation of ozone is higher. So even though there's not very much tropospheric light at short enough wavelengths for the photolysis of ozone, there is enough of it where the quantum yield is high to photolyze ozone around 290, 300 nanometers. So it's dependent upon the actinic flux, the absorption cross-section, and the quantum yield. So you have to have all three for the photolysis rate of ozone to be high. So for J, O singlet D, and J, O triplet P, they're the photolysis rates of ozone to O singlet D and to O triplet P. You need to have absorption of light at wavelengths less than about 300 nanometers. So if you look here, the quantum yield of ozone, you can see, right, this is in reverse. This is the amount of energy in a photon. So which photons have got the greatest energy? High wavelength or low wavelength? Low wavelength. So with the energy going up, the wavelength goes down. So you can see here, this threshold here is about 300 nanometers. It's about, you can see here, it's about 300, 310. You can see it very, very sharply falls to nearly zero. Because it falls to nearly zero, and we already know that most of the radiation in the troposphere falls to nearly zero below, you've got a point around 300 nanometers where photolysis can happen in the troposphere. What about in the stratosphere? Well, you can see here that at 30 kilometers, you've got radiation below 220 and down to about 280. And you can see here, 280 to 300, the quantum yield of ozone is nearly 1. And so that says that in the stratosphere, you get nearly 100% photolysis of ozone when it absorbs the photons that are there in that range. So that allows you, because your actinic flux is high enough, as a function of the short wavelength, because your absorption is high enough and your quantum yield is high enough, that means that you can have the photolysis. But in the troposphere you can't. Is that clear? Does anyone have any questions about that particular side of it? So, this here tells you something about the amount of O singlet D and OH in the atmosphere. So the O singlet D is... Got any pens? So the ozone plus a photon, what's the product? Sorry? O2? Okay. O singlet D and O2 plus O triplet P. Which one's the high energy? The other one. Singlet D is the high energy one. Okay, triplet P is ground state. Okay, singlet D is the excited state. And singlet D plus water goes to 2OH. So, from this figure here, you can see the singlet D and the OH concentration. And you can see that they increase as a function of height. So why do they increase as a function of height? More of this. Why is there more of this? Strong solar radiation, high quantum yield, high absorption cross-section. So all three things are happy. Because of that, you get your O singlet D. Why is the OH not even higher? So if you see here, the OH has a particular value. If there were more water vapour, you would have even more OH. But as you go up through the atmosphere, you get drier. So the stratosphere has less water, and so the limiting factor for your OH production is the amount of water vapour you have in the atmosphere. So this requires wavelength of the right, light of the right wavelength, quantum yield to be high enough, and enough light. And in order to produce this, you need enough water vapour. In the troposphere, just to recap, there's enough light just at the wavelengths of 290, 300, 310, where the quantum yield is sufficiently high to have some ozone absorption and some sub-ozone photolysis, and there's much, much more water vapour. And so you're not limited by the water vapour in the troposphere, you're just limited by the number of photons of sufficiently high energy. It's good. I was hoping that this was not permanent. Okay, good. So, the threshold wavelength for photolysis. What do you need for photolysis? Just to recap, you need enough light of sufficient energy, which means sufficiently low wavelength, to be able to break the bonds. And here's an example of the calculation that you can do to work out the threshold energy you need for a photon. So, the energy, so what's the energy of a photon? How do you calculate it? So what's that H? What's the H in the first? Is anyone? Planck's constant. Okay? You familiar with Planck's constant? Okay. So what's this? Okay. So Planck's constant times the frequency. So that's Planck's constant times the speed of light divided by the wavelength. So Planck's constant there, speed of light. So that means that the wavelength is Planck's constant times the speed of light divided by the energy. We know the bond energy for something like the hydrogen molecule is 436 kilojoules per mole. So 436,000 joules per mole. For one molecule, so what's this? Avogadro's number. So to get from moles to molecules, you divide by Avogadro's number. So for one molecule, the amount of energy in the single molecular bond in hydrogen is 7 times 10 to the minus 19 joules. So the wavelength, which is Planck's constant, times the speed of light, divided by the energy of the bond, tells you that that is the threshold value for the photolysis, so the photodissociation of molecular hydrogen. So where does that happen in the atmosphere? Okay, so 274 nanometers. Where can you see 274 nanometer light? So where? 10, 20, 30, 40, 50 kilometres? Up? Well, 274 nanometres is roughly there. So there's almost nothing at 30, but there's plenty at 40. So molecular hydrogen will photolyse between 30 and 40 kilometres and upwards. So who are the quick ones? Who can tell me what the threshold wavelengths are for oxygen and nitrogen? Can anyone spend a little time and do those calculations for oxygen and nitrogen? Have you got your calculators with you? So there's a table of the bond energies. I'll give you a couple of minutes. Shout out if anybody's done the calculation. 195 for the NO. Ah, right, okay. So you're looking at a nitro compound, not molecular oxygen or molecular nitrogen. What you're doing is, you're right, that is about right. So if you had a nitro compound in the atmosphere, it would absorb somewhere in the long visible wavelength range.
For oxygen is 240.
240? Yeah.
The other one is twice the triple bond.
So is it a triple bond?
Because
Yep, you're right.
yeah. It's 127.
Okay. 240 and 127. So does that tell you anything about why there's lots of N2 and lots of O2 in the atmosphere? (240). So where can you photolyse oxygen in the atmosphere? Must be above about 40 kilometres. Okay? So where can you photolyse nitrogen in the atmosphere? Well, outside the atmosphere. Where there is, if you look, you don't have sufficient photons of sufficient wavelength unless you are extraterrestrial. So you can photolyse it in space. Yeah? Is there much nitrogen in space? No. You need an atmosphere. So you need the gravitational pull of the Earth. So you can't photolyse N2 in the atmosphere. You can photolyse oxygen above 40 kilometres, about the same places you can photolyse hydrogen, but you can't photolyse nitrogen anywhere. So you might take a look at that web link there just to recap on some of the threshold calculations. So this is in the presentation that's on Blackboard now, so I've changed that presentation. So if you want to download the new one, it's in there. Okay. This table here, why do you think that anybody has tried to calculate the photolysis thresholds and photolysis cross-sections and photolysis rates of these compounds?
We need to calculate the rate coefficient.
Okay, so they're calculating the rate coefficients. Why those compounds? Why do they care about those compounds?
Ozone depletion.
Yeah, okay, so they're all ozone-depleting compounds and intermediates and reservoirs. And you can see that they've calculated here the photolysis thresholds and the lifetimes at Z equals 0, so that's the ground, and at Z equals 20 kilometres, so that's the just above the tropopause, so in the stratosphere. So those are the sorts of calculations you can do to work out where you're going to absorb light, and with the quantum yields, where you're going to photodissociate the compounds. All calculated from simple calculations of the bond strength and the relationship to the amount of light in the atmosphere. Right, so is everybody happy with photolysis? You're not going to need to do any direct calculations of actinic flux. If you were being asked to do calculations, it would simply be based around the fact that you've got absorption cross-section, quantum yield, and actinic flux, that this is the sort of profile through the atmosphere of the actinic flux, that this is something that represents absorption cross-sections, and this is quantum yield, and these are how you calculate bond energies. So photolysis is fairly simple as a concept. So is there anything that anybody's unclear about that you'd like me to clarify before we move on to gas kinetics and how collisions between molecules occur and how fast they occur?
Do we need to integrate the wavelength only?
So how would you integrate? If I was to ask you to integrate a function, would that be fair of me? To try to integrate a complex function across all wavelengths? You need a computer model for it. And I won't ask you anything about integrating the complex functions to get actinic flux or the integral of actinic flux times quantum yield times the absorption cross-section. It would be I might ask you, is there enough light at this wavelength if this is the quantum yield and this is the absorption cross-section? So I don't think it's fair for me to do that, because nobody has got a computer up here. It's too complex to do in your own head. Okay? I'd like to ask you a question, but it's not possible to answer it. Okay? I might give you the answer to the integral. If I give you the answer to the integral and say, would you expect this to photolise, and where would it photolise, I can give you a table of the integral. So there's different ways, but you wouldn't be expected to be able to calculate the integral because it's too complex. Okay? Well, let's move on and see if we can reach an understanding of gas kinetics. So has everybody come across these four terms? Initiation, propagation, branching, and termination. Okay? It's good then. So, what's an initiation reaction? What does that do? What is initiation? What's the terminology, the definition mean? The start. Okay? So it's just the start of a reaction sequence. So all reactions in the atmosphere ultimately get their energy from one place. So where does the energy come from? The sun. It doesn't matter if the incident radiation is direct, or it's radiation coming from the bottom, or it's heat. It could just be a thermal reaction. But ultimately, all the energy in the Earth comes from the sun. Excluding a bit of nuclear energy and this kind of stuff. But let's say everything in the atmosphere comes from the sun. So all initiation reactions could be thermal reactions because of the temperature of the atmosphere, or photolysis reactions. So propagation. So I've put something in brackets there, conversion between radicals. Why is propagation normally a radical reaction?
Because we can produce another radical.
That's true. Because you start from radicals, because most photolysis produces a radical. So what is the radical species here? O singlet D is a radical species. Okay? Propagation, conversion between radicals. Which are the radical species in this first one? OH and CH3. So what's CH3? Does anyone know what sort of radical that is? It's the methyl radical. So it's just from methane. Okay? And what's the radical species here? So what's that called? It's the hydroperoxy radical. Okay, so hydroperoxy radical, and it produces the OH radical. So here, the OH radical plus methane produces the methyl radical plus water. Here, NO plus the hydroperoxy radical produces NO2 plus the hydroxyl radical. So propagation is just a conversion between radicals. And it carries on. Propagation just carries on. Sometimes you can get multiplication of radicals. So if you remember, O singlet D that is produced from your ozone reaction can react with water and produce two OHs. So you start with one radical and you produce two radicals. So not only are you propagating, you're increasing. So it's a chain reaction. So what stops reaction sequence? It's the death of radicals. How do they die? They can recombine, or they're scavenged. So it's very simple: initiation, propagation, branching, and termination. And you keep going through this cycle. And depending upon how many reactants there are to terminate, that will determine how long the chain of propagation and branching is. Do we know what one of the major I was going to say something wrong then, sorry. What I was going to do was say something a little controversial. Is ozone a radical? Is it closed shell? Yeah, it's very close to being a radical. It's a very reactive species. I was going to talk about termination, but I was going to give the wrong example, so I won't bother. I'll leave it to some of the later examples. But initiation, propagation, branching, and termination. So an example of this, or a schematic that represents this. If you start with a compound X and it photolyzes, or it gets excited to become a radical species, reacting with oxygen, your propagation reaction could be the reaction of the radical with oxygen to give you your peroxy radical. You can react lots and lots of different times with other interconversion of radical species and end up with termination to something like an oxide. And the end products can be something like aldehydes, ketones, peroxides, acids, and nitrates. So what happens if you've got okay, so what sort of reaction was this one? Yeah. NO2 plus OH. So what sort of reaction was that? Yeah, it's a propagation reaction. Does anyone know what alternative reaction for HO2 competes with this in the troposphere? What's a main competing reaction for the hydroperoxy radical? So, what's this? Does anyone know what this is? That's hydrogen peroxide. Okay? What sort of reaction is this? It's a termination reaction. So this is a propagation reaction. So if you've got lots of NOx, you have lots and lots of reactions of HO2. So the propagation, the chain length, is the chain length longer or shorter with high NOx. Do you know what chain length is? Chain length is how many times it goes round the reaction chain. And it can go round and round this reaction chain when the NO is higher many, many more times than when it's low. Because otherwise, the HO2 can react with itself and it will terminate the chain. So the radicals have died. The radicals have gone when they form this. Does anyone know what happens to this? Sorry? Well, it can photolyze to produce OH, two OHs. I don't think it reacts with itself. But normally what happens, it sees water or it sees the ground and it's deposited. So it's lost from the chemical system. So termination is normally when something forms a stable product, and these stable products, if they have long lifetimes because they're stable, they can be lost from the system. So it's the death of radicals and the loss of the chemical reactants from the system. So how fast do these reactions happen? So consider A plus B equals C plus D. What is Na, Nb, Nc and Nd? Right. In this case, they're not the stoichiometric coefficients. Okay. Normally they are. So I do apologise, it's kind of ambiguous notation here. This is just the number of molecules of A plus number of molecules of B, number of molecules, because what we're doing is using those in the rate coefficients. Okay? No. Reverse that. I use it ambiguously different way later. That is the stoichiometric coefficients, you're right. Okay. In this case, it's stoichiometric coefficients. Watch for later where I use it wrongly. Okay. So the stoichiometric coefficients. So what is a stoichiometric coefficient?
It's the amount of products or reactants that is produced or consumed during unit amount of reaction.
Yes, and it's dependent, yes. It's basically the governing equation for the chemical reaction, which tells you the amount of material that is either consumed or produced within that reaction. So in order to calculate the rate, you can see this is dependent upon 1 over the stoichiometric coefficient times the deconcentration by dt of the reactant or the products.
Is there any fundamental law that we write down to describe these reactions? Not really. They're normally all described in an empirical way. The reason they're normally all described in an empirical way is that they're all essentially discrete individual reactions that have quite a complex requirement on their electronic, or dependency on their electronic structure. So the rate proportional to a concentration raised to the power of, well, raised to a finite power. And the order of reaction is the sum of those powers. So if the rate is proportional to A plus B squared plus C cubed, A, B squared, C cubed, D to the fourth, what is the overall order of reaction? 1 plus 2 plus 3 plus 4. Okay? If that's true. It's almost never true. That was just a crazy example. But the order of reaction is the sum of the powers to which the concentrations need to be raised. So elementary and non-elementary reactions. Are you familiar with the concept of elementary and non-elementary? Elementary is the simplest form to which you can express a reaction. You can't break it down into any simpler process. And non-elementary are if you sum, if you say, for example, if it's A plus B going to C plus D would be the elementary reaction, or C plus D going to EF would be an elementary reaction. A plus B going to EF will be a non-elementary reaction, because that could be broken down into these simpler parts. So quite often you can get these lumped reactions that are talked about and given a reaction rate. You could have a reaction rate for a non-elementary reaction that is made up from the reaction rates of 2 elementary reactions, or 3 or 4 elementary reactions. So if I gave you this reaction rate, you wouldn't know if it was because this was fast. You wouldn't know whether the rate of this was because this was fast and this was slow, or this was slow and this was fast. Because if this was slow, it would be determined by the slowest part of these reactions. It doesn't matter how quick A plus B turns to C plus D, if this happens at an infinitesimally small slow rate. Because that would mean that this is produced at an infinitesimally small rate, even though this is consumed at a very fast rate. So you could measure A and it decreases really quickly. And you could measure B and it decreases really quickly. But you could measure EF and it's produced really, really slowly. Because this reaction is really, really slow. So that's the complexity of a non-elementary reaction. So we need to be careful that we can't break reactions down into simpler elementary forms when we're considering reaction rates. So here, really simple reaction. 2NO plus oxygen goes to 2NO2. So we know there are 2NO, the stoichiometric coefficient here, that's here. The stoichiometric coefficient for the oxygen is 1, so it's just 1 there, and the stoichiometric coefficient for the NO2 is 2. So the rate of consumption of NO is considered there, consumption of O2 there, and production of NO2 there. So oxygen is lost at half the rate as NO is. You can see that directly because of the equation. You need 2 NOs for every oxygen molecule that's consumed. And so therefore, if you've got 20 ppb per second of NO consumed, you've only got 10 ppb per second of O2 consumed. And you'll form 20 ppb of NO2. It's quite clear from, yeah? It's fairly straightforward. So NO loss is twice the loss rate of oxygen. So methane plus the hydroxyl radical. The stoichiometric coefficients of everything are 1. So you can see there, they're all lost at the same rate and produced at the same rate. So here are a whole bunch of first order, second order, and third order reactions. So remember that the overall order of reaction is the sum of the exponentials in the rate dependencies. So a first order reaction, A going to B plus C. The kinetics is described. What's the stoichiometry with respect to A in the top expression? It's 1. Yeah? So therefore, it's 1 over 1 times dA by dt. And the unimolecular rate constant is K unimolecular times A, and that's a first order rate constant. So the units of a first order rate constant are per second. So it's an amount of molecules are being destroyed at a rate of per second. So if you look at the first example there, this here is a peroxynitrate, and it decomposes. What's this species here? Does anyone know what that is? What sort of species is it? It's a radical. It's a methyl peroxy radical. And NO2. So what sort of reaction is this? Not what order, what sort of reaction? Initiation, yeah. So what you've got there, you've got a reservoir species of 2 radicals, and because of temperature, because of heat, so the energy here is temperature, you get a thermal decomposition first order reaction that produces 2 radicals. And then, well, sorry, NO2 is not a radical. Produces a peroxy radical and NO2. And this one is a photolysis reaction, and again is an initiation reaction. So quite a lot of initiation reactions are unimolecular. Okay, so they're not the reaction of 2 stable species, they're the decomposition. So the thermolysis, which is thermal decomposition, or photolysis. So they're both initiation reactions. So often the other reactant, so what's the other reactant in this case? It's NO2 plus H mu. Yep, so it's a photon with an energy of H times mu. So what's the other reactant in this case? Heat. Yep, so it's the enthalpy of decomposition of this peroxynitrate. Sorry, yeah, peroxynitrate. So bimolecular rate constants. So you've got A plus B plus C going to C plus D. So what's the stoichiometry with respect to the reactants and products here? So it's 1 in all cases. So the dA by dt equals dB by dt equals minus, because it's a destruction, so it's minus, this is a consumption of A times B. So your units of a bimolecular reaction rate are centimetres cubed, or volume, divided by per molecule per second. So when you multiply it by the two concentrations, you get the product per second. So the number of molecules per centimetre cubed per second. So this pair of reactions both of these actually. What are these reactions? What sort of reactions are these? No. They're both propagation reactions. OH is a radical and C2H5 is a radical. That's the ethyl radical, that's the hydroxyl radical. This is an ethyl peroxy radical, that's an ethyl peroxy radical. Does anyone know what this is? It's an alkoxy radical. Okay? So this is two peroxy radicals forming an alkoxy radical. And this is a standard integral where the concentration of A is the initial concentration of A divided by Kt to the A0 plus 1. And we'll move on to the termolecular, the third order, three-body reactions. So first of all, what's the M? The M is the third body. It's an inert third body that doesn't take part in the reaction, but it's necessary for the reaction. And because it's necessary for the reaction, then the overall reaction rate includes the concentration of M. So normally M is something like nitrogen or any other molecule that doesn't react in the atmosphere. So third body reactions, are they normally faster at the ground or higher up? At the ground, because M is higher. Because the concentration of high pressure is higher, so these are pressure dependent reactions. And so near the ground, your termolecular reaction rates are normally quicker than they are quicker than they are higher up. So dA by dt equals dB by dt equals the termolecular reaction rate constant for the destruction of A and B times concentration of A, B and the third body. And the units are centimetres to the power 6, molecule to the minus 2 per second. And if you look at these reactions, what sort of reactions are these? termination reactions. So a lot of your termolecular reactions are termination reactions, and a lot of your termination reactions are three-body reactions. So this is the death of atomic oxygen, and this is the death of chlorine oxide. So if you remember, we're talking about the death of radicals for a termination reaction. Now this is only a temporary death because it forms chlorine nitrate. So what does so ClONO2, what does that do? Yeah, how does it do it? Photolyzes. Okay, so it's an initiation reaction by the photolysis of that reservoir, gives you ClO, and the ClO then reacts with the ozone. And so you end up with an ozone destruction cycle. So you end up with a termination, forms this reservoir temporarily, and then a bit later on, your photolysis of that reservoir leads to the chain propagation and the destruction of ozone. So termolecular reactions are not elementary reactions. So remember that. They are not normally three things hitting each other at the same time. So termolecular suggests A hits B, hits M. So it suggests that there's a molecule of a molecule of B, and a molecule of M, and they all hit each other at the same time. That's not true. What often happens is A hits M, forms a complex, and that hits B, or A hits B, and the M also hits it. And so you end up with multiple ways that a termolecular reaction can occur. It's not normally an elementary reaction. So in this case, it could be A plus B leads to an excited complex AB, which then hits M, which collisionally deactivates it to form your final product, AB. So the M just ends up being a sink for the additional energy in the excited AB. So are you happy with unimolecular, bimolecular, termolecular, initiation, propagation, branching and termination? So they are the classes of reaction, the types of reaction, the order of reaction, and how. So if you were given a reaction rate and it had units of centimetre sixth molecules to the -2 per second, you would know it's a termolecular reaction. If you were given units of per second, you know it's a unimolecular decomposition, thermal decomposition or photolysis, etc. Happy with that? Good. Let's keep running through some examples. I want to kind of drill this in so that you're familiar with the types of reactions and the sorts of reaction rates. So NO plus ozone. You think that's fast or slow? NO is actually a very good sink for ozone in the troposphere. Quite often. Would you say a city has high ozone concentrations or low ozone concentrations normally? Sorry? Normally quite low in the city because it's close to strong NO sources. When you go downwind of the city, where the NO to ozone ratio, because you're not close to high emissions of NO, NO is quite reactive, and so it falls down as you move away from a city, so your ozone goes up as you move away. So you can have polluted regional background of ozone that's high, but in the city, normally your NO sees your ozone and it eats it. So you end up with ozone holes over cities. So normally the secondary products are quite low, but the primary pollutants are high in the city. Normally because of this NO plus ozone reaction. So dNO by dt
is the bimolecular rate constant for the destruction, so minus K bimolecular, times the NO concentration times the ozone concentration. And that rate at 300 Kelvin is 1.8 times 10 to the minus 14 centimetre cubed per molecule per second. So the clean troposphere, the NO is 0.1 ppb, and ozone about 30 ppb. What is the loss rate of NO at 760 torr? Well, it's 3.23 times 10 to the 7 centimetre molecule per centimetre cubed per second. And that's the loss rate, dNO by dt. So it's a really simple calculation. So if you were all fed that sort of information, could you all calculate that reaction rate? Good. Really quite straightforward. Now, the change in ozone is really small compared to that of NO. Why is that? Because the loss rate of NO is the same as the loss rate of ozone, because the stoichiometry is the same. The concentration of ozone is very much higher than the concentration of NO. And so we can treat the ozone as a constant. Okay? If you see there, the ozone is 300 times higher than the NO. So in this case, when it's in a clean troposphere, we can treat this as a pseudo first order reaction. So do you understand what assumption we've made there? If one reactant is in very, very high excess compared to the other reactants, and they've got the same stoichiometry, then the loss rate of the high concentration reactant is really, really small. So you can consider that the overall reaction happens at the constant concentration of the high concentration reactant. So this brings us to the concept of the pseudo reaction order. Do you understand what I mean by pseudo? So pseudo is, it's not really, the elementary reaction isn't really first order, but you can assume that one of the reactants doesn't get consumed anywhere nearly as quickly as the other reactant, and so it's first order with respect to the quickly reacting reactant. So NO plus ozone very much higher than NO. We had 30 ppb. So what's 30 ppb at 760 torr? Do we know how many molecules there are? Right. Quick recap. How many molecules are there at the total number of molecules at the ground level in the atmosphere? What's the concentration? 2.5 times 10 to the 19. So what's 1 ppm? 1 part per million. Two and a half times 10 to the minus 30. What's 1 part per billion? 2.5 times 10 to the 10 to the 10. What's part per trillion? 2.5 times 10 to the 7. Okay? So to get to a mixing ratio, you just divide by the number that's in that mixing ratio. Million. Divide by a million. So 2.5 times 10 to the 19 divided by a million. 2.5 times 10 to the 19 divided by a billion. 2.5 times 10 to the 19 divided by a trillion. And that will give you the concentration. So 30 parts per billion of ozone. 30 parts per billion is 7.3 times 10 to the 11. Okay? Roughly. And the NO then
at 0.1 part per billion is 2.5 times 10 to the 9. And we have the loss rate, the bimolecular loss rate, would be this. But if we assume that ozone stays constant, because it's not consumed anywhere nearly as quickly as the NO, in terms of its initial concentration, it becomes a pseudo-rate order coefficient, where the bimolecular rate constant times the ozone concentration equals K prime. And what are the units of a first order rate coefficient? Per second. Okay, so this tells you the rate at which the NO is consumed, because we've got K prime times the NO concentration. It's 0.14 per second. So, that's how we use a pseudo first order rate assumption. What about pseudo second order? So what sort of reaction is this? Does anyone understand what sort of reaction this is? What's the order? It's a third order reaction, so it's termolecular. Okay? So HO2 plus HO2, but also OH plus OH. So if you see this peroxide, yeah? Peroxide is formed from HO2 plus HO2. What's the order of this reaction? This is second order. And this one is a third order reaction. So this one here is pressure dependent. This one here is not pressure dependent. Okay? This one depends on M. But if you look at this reaction, what's the concentration of OH in the atmosphere? Roughly. Ground level OH concentration. Anyone got an idea what it roughly is? 10 to the 6 molecules per cc, roughly. So 10 to the 6, 10 to the 7, something like that. So 10 to the 6 with M is 2.4, 2.5 times 10 to the 19 that we just talked about before. So this is really high number, and it's constant because it's produced and consumed in this reaction, because it's just there as a collisional deactivation molecule. And so we have OH plus M can be represented not by the termolecular rate constant times the OH squared times the M, but by an effective rate constant times OH squared. So this is simply a pseudo second order reaction in OH concentration. So we don't need to consider the M in this reaction because it's not consumed in the reaction. So you can consider at any one pressure that you've got a pseudo second order rate coefficient, which is the K times the termolecular rate times the M. So if you were asked, if you were given the concentrations of reactants and you were given their bimolecular or termolecular reaction constants, could you turn them into pseudo first order unimolecular and pseudo first order bimolecular rate constants? Do you understand why we're doing this? Or do you understand the process by which we're making the assumptions? It's if one of them is either in very, very great excess, and it is not consumed as quickly, or it's not consumed at all. And so then you can turn it into a pseudo simpler rate coefficient. So it doesn't change the overall order of reaction, it just changes the way that we can calculate the rates. We just assume one of the concentrations is constant. Has anyone heard about photostationary state? So what is this? If you look at those three reactions, what is the sum of those reactions? NO2 on the left, NO2 on the right. NO on the left, NO on the right. O2 on the left, O2 on the right. O on the left, O on the right. So it's nothing. Nothing happens. So if you had just NO2, ozone and NO in the atmosphere, nothing would happen. Is that correct?
Nothing would change.
So you'd always have the same concentration. It's true. Nothing would change. If your sun did not come up or go down. If you didn't have clouds going across. If your temperature stayed the same. If your pressure stayed the same. Then the net sum of these three reactions is nothing. So it's stationary, because it's stationary, nothing happens. And it's dependent upon the light, photostationary. So it's dependent upon this rate constant, which is a photolysis rate. If this changes, what happens? So if it gets brighter, if the sun comes out, so if the sun comes out, what happens? So there's more NO and there's less NO2. Because this thing has changed. This reactant in the first reaction is changed. So if we consider the production rate and loss rate of NO2, can you see NO2 on the left here means that the loss rate of NO2 is minus JNO2, that's the photolysis rate, times the NO2 concentration. And the production rate is NO times ozone times the reaction rate between these two. So dNO2 by dt is the production rate minus the loss rate. But if nothing changes, okay, so if the sun stays out, if it stays at the same temperature and we stay at the same pressure, then dNO2 by dt equals 0. Which means that JNO2 times NO2 equals K3NO times ozone. So you can just divide by the JNO2 and calculate the NO2 concentration. It's just your K3NO times ozone divided by JNO2. Or you can calculate your JNO2. Or you can calculate your NO concentration. Or your ozone concentration. So because they're all in this photostationary state, you only need the instantaneous concentration of any two of them and the rate constants to calculate the others. So this photostationary state is actually quite a powerful assumption. So you don't need to measure everything, you just need to measure a couple of the parameters. And you can rearrange because the production rate equals the loss rate of each of the compounds, because they don't change in concentration. So instead of saying dNO2 by dt, you can also just say dNO by dt. And you can do the same calculations. So this photostationary state can be calculated from the NO concentration, from the dNO by dt, or dNO2 by dt, or d-ozone by dt. And you can know everything about the system really quite quickly. But that doesn't mean that everything's got the same lifetime. Do you know what we mean by lifetime? Chemical lifetime of compounds. Let me just see, I want to see, I think this will probably be the last concept we want to touch today, and then we'll just go through a few examples and try and recap. Because otherwise there's probably a few too many concepts to have in one lecture. But I do want to see if you can grasp the concept of a lifetime. So what does it tell you? The clue's in the name. What does it tell you? What does the lifetime of a compound tell you? How long it lasts in the atmosphere? Yep. Now, because, I mean, you can see from these reactions that there are, I thought I'd say multiple, I've only written one equation for each species. What's the lifetime of HO2 doesn't just depend upon this reaction. It would also depend upon this reaction. So the lifetime is not just from one reaction. It's from all of the reactions that could consume a compound. So the lifetime of HO2 with NO might be 1 minute. The lifetime of this HO2 with itself might be 1 minute under certain conditions. What would the lifetime of HO2 be with both reactions? More than 1 minute or less? Less. So basically, your lifetime decreases the more reactions you have. So you've got to be able to calculate what the overall lifetime is according to the sum of the reactions. Now, first order reactions, the unimolecular ones, are simply A going to products. So this might be thermal reaction or a photolysis reaction, and it just produces the products. And the lifetime is just 1 divided by the unimolecular rate constant. What's the units of unimolecular rate constant? Per second. So what's the units of lifetime? 1 divided by per second, seconds. Okay? 1 divided by seconds to the minus 1 is seconds. So it makes sense that a first order reaction lifetime is 1 divided by the reaction rate. What's a second order lifetime? Well, the lifetime of one of the reactants is 1 divided by the second order rate constant times the concentration of the other reactant. So what happens if the concentration of B goes up? The lifetime of A comes down. Okay, the more of the other reactant there is, the more collisions you can have. So the quicker your reaction can happen. That doesn't mean you have more of A made, it just means it's being made more quickly. So the reaction rate is dependent upon the concentration of the other reactant. And for third order reactions, the lifetime is dependent upon 1 divided by the term molecular rate constant times the concentration of the other two. So what's the units of reaction of a bimolecular? Units of rate of a bimolecular reaction? Centimetre cubed per molecule per second. So therefore, 1 over the lifetime is per centimetre cubed, molecule per centimetre cubed per second. And then it's multiplied by this concentration to get back to per second. Okay? And it's the same for the term molecular. So you've got centimetre to the 6th, molecule to the -2 per second, times molecule per centimetre cubed per second, times molecule per centimetre cubed per second, equals per second. 1 divided by per second equals seconds. So you just need to remember that the lifetime of a reactant is dependent upon the concentration of the other reactants. If it's bimolecular, if it's unimolecular, then there are no other reactants, so it's a constant. If it's bimolecular, there's only one other reactant, so it's 1 divided by the constant times the reactant concentration. If it's termolecular, there are 2 other reactants. So what is the lifetime of NO with respect to the reaction with NO3, with ozone? So what's the lifetime of NO with respect? So what's the lifetime of NO there? Is it bimolecular, unimolecular or termolecular? Okay, it's bimolecular. Yep, it's 2 molecules, bimolecular. What is the lifetime of a compound with respect to a bimolecular reaction? One divided by the reaction rate times the concentration of the other reactant. So what's the lifetime of NO with respect to ozone here? Does anyone do the calculation? So we have 1 divided by K divided by ozone. So it's 1, this is 1.8 times 10 to the minus 14. What's the ozone concentration? Something like that. So what's the answer to that? So it's roughly ish, is that about right? Has anyone done the calculation? 1 divided by 1.8 times 10 to the minus 14 times 7.3 times 10 to the 11. That's 10 to the minus 3. That's roughly 10. So that's roughly 10 to the minus 2. So it's roughly 100 seconds. Something like that. I haven't done the calculation, so someone else is going to have to tell me. So it's order, so So 76 seconds. So what does the lifetime mean? Does that mean that your NO disappears to 0 in 76 seconds? Disappears to half its concentration in 76 seconds? Does anyone know what happens? What does the lifetime mean?
The expected lifetime for every molecule.
Okay. It's actually called the E-folding lifetime, because I don't want to do the derivation for you because you don't need to know it. But all it is the integral, the standard integral for the rates equation is an exponential. And so 76 seconds is the time for the concentration of NO at time t equals the concentration of NO at time 0 divided by E. Okay, so it goes down by a factor of 2.7 roughly in 76 seconds. So that is the E-folding time. I tell you what, next week, not next week because it's aerosol next week, but the week after we will do the derivation of this. So somebody go away and have a look at why this is the E-folding lifetime in, I like that. Okay, go away and find out why that's the E-folding lifetime, because I've actually given you all of the information. So why is it an exponential function, and why is this the lifetime for the reduction of the concentration by a factor E? Does anyone know how to go and try and find this? The answer is based around this. Okay. So that's the example with respect to the reaction with ozone. But the lifetime for multiple first order loss processes, so you might imagine the lifetime of methane with respect to reaction with OH, NO3, photolysis, etc. The K total is K1 plus K2 plus photolysis plus K3, etc. So the lifetime, 1 over the total lifetime, is the sum of 1 over the lifetime with respect to reaction 1 plus 1 over the lifetime with respect to reaction 2 plus 1 over the lifetime with respect to reaction 3, etc. So it's the same as, presumably you've done resistor networks in electrics, so it's basically just Ohm's law. It's just the sum of the resistances. I've got the answer to your... Right, the answer to this E-folding lifetime. I forgot I had this. Right, okay. So essentially, all you're doing when you're expressing the bimolecular reactions, so if you remember, we were talking about how reaction rates were expressed in terms of empirical relationships. We weren't normally describing them in fundamental terms. And you can see here how normally, have you come across Arrhenius expressions, chemical reactions, activation energies? Is this something you're normally familiar with from chemistry? Where the rate constant is normally plotted as a function of temperature here, and you can expand the rate constant into a prefactor and an activation energy divided by the gas constant times temperature. So this energy for the reaction, the activation energy, 14 kilojoules per mole, the A factor is in terms of centimetres cubed per molecule per second because it's the intercept, and K is this 1.88 times 10 to the minus 12 with an exponential term. So the activation energy is the amount of energy for the reactants to get over the barrier to forming the products. So this energy term, 14 kilojoule per mole, is this energy from going from OH and methane separate. So what's the product of OH plus methane? HO2 plus methyl radical. OH plus CH4 goes to HO2 plus CH3. So what sort of reaction is that? Propagation. No, branching, you're right. Two radicals. Yeah. Radical plus stable goes to radical plus radical. Yep, the branching reaction. So if your products are down here and your initial reactants are here, your activation energy is what is necessary to make the products happen, which means they must get over the energy barrier in the chemical system. So that energy barrier, essentially, the fraction of molecules that can get over there as a function of temperature is much greater at higher temperatures because your kinetic energy goes up. So what is your kinetic energy? No, I won't say that. No. Okay, so your kinetic energy goes up with the more thermal energy you've got. Okay, so the more heat you've got, the more molecules you have that get over this barrier. So therefore, your E to the divided by RT, when your temperature goes up, the exponential goes down. Okay? So you can also have negative activation energies. What does a negative activation energy mean?
It will automatically.
Yeah. It basically says that the temperature is high, that it will happen whatever the temperature, and your product distribution has no barrier to being formed. So you put reactants in there and you'll spontaneously get your products. So there's a couple of examples of negative activation energy reactions. So, we've done photostationary state. We've looked at steady state assumptions. So what was the steady state assumption again? Do you remember? Concentration stays constant. So what does that mean about production rate and loss rate? They're equal. No, they equal each other. So the net production rate is 0. The net loss rate is 0. Production rate equals the loss rate. That's the steady state. So what's pseudo steady state? I tell you what, I am noticing that you are probably falling asleep from too many different concepts. Would you agree that we don't need to introduce any more for today? Or are you quite happy to go on for the next 10 minutes and finish this? I would suggest what we do is recap and then move on from this point next time. Are you happy with that? I'm getting more nods than shakes. I'm a Democrat, so I'm quite happy to go with the consensus. Are you happy? Right, what I want you to do is go away and look at other people's ways of telling you what I did today. So look on the internet. There's, in some of the books, in the standard books, there are different ways of expressing this. But make yourself completely familiar with reaction order, types of reactions, photostationary state, steady state, pseudo-reaction order, recap on the photolysis rates, because these will underpin the gas phase chemistry and all of the examples we'll move on from. So can I ask, before we leave today, how much of the material that I covered today did you already cover in previous lectures?
80%.
Sorry?
80%.
80%. Yeah? Is that right? So you should be familiar with all of the concepts. Are you comfortable with all of the concepts? Great. Okay, so maybe I'll start teaching you something soon. Now we've done all the conceptual stuff. Okay, good. Right, I'll see you next week. I think the week after I'm in India, so do you know Hugh Coe? So Hugh will probably be lecturing for me, but I'll give him the lecture material. So he'll be doing this next lecture on the gas phase. Okay? All right, thanks very much. Who's got the gadget? Anyone else? Okay, so you go away.